Hello everyone, and welcome to the YEA F equals MA lecture series. This is the fourth lecture, and we'll be talking about dynamics and Newton's laws. So first, let's briefly go over Newton's laws. So Newton has three very famous laws. The first one is that a body in motion stays in motion and a body at rest stays at rest unless it's acted upon by an unbalanced force. This is also basically describing the concept of inertia, that if something's moving, it will keep on moving if nothing else happens to it. And if it's at rest, it just like won't start moving randomly for no reason. And what would cause something to start moving just randomly would be a force. And so if we want to go deeper into this, we need to go to Newton's second law, which formally states that the rate of change of the momentum of something is equal to the total force acting on it. And this is kind of fancy. It involves momentum and all that. But for now, all we need to know is that if the object has a constant mass, which it almost always will in F equals ma problems, then you can just use the normal form, which is that the net force is equal to the mass times the acceleration, or F equals ma. That's where the name of the contest comes from. Alright, now there's the third law, which is if if we have two bodies that are interacting, and one of them exerts a force on the other one also has to exert an equal and opposite force on the first one. So if we have if we have A here, let's say this is A, and then this is like B. If A exerts a force on B like this, then we must also have B exerting a force on A, which has an equal magnitude and it's in the opposite direction. And out of these three laws, so far the most important one is the second law, because it allows us to relate all of the forces that we know to an object's acceleration. And I will go over all the forces that you might encounter later on in this lecture. So for now, we'll be basically using the second law to see what the forces on objects are, and then after we add them up together to get the net force, we can find its acceleration. And then after that, we can use that to use our kinematic equations, and then, if needed, to solve the problem. Alright. But before we talk about types of forces, we need to talk about free body diagrams. What is a free body diagram? Well, it's just a very useful way of visualizing all the forces that act on an object. So, for example, in our object here, we have two forces. One of them's like over here, it's acting that way, and the other one's over here, it's acting upwards. And so if we draw a diagram like this, it would be pretty easy to visualize like all of the forces that are acting on the object. And this is very useful because F equals ma only applies to really the net force. So in order to use F equals ma, we first need to draw our free body diagram and then add up these forces to get the net force. So in this case, our net force would be somewhere along here. And then after that, we just divide this by the mass to get its total acceleration. And as the problems get harder and harder, drawing free body diagrams get more and more important, and they will greatly make make the problem much easier. All right, now let's talk about forces. So, first of all, let's talk about gravity. And we briefly introduced gravity when we were doing projectile motion, and we said that all projectiles accelerate downwards near the surface of the Earth because of gravity. More formally now, we will say that the force of gravity on any object near the center of the Earth is mg downwards. M is the object's mass, and g is a constant, which is the acceleration due to gravity near the center of the Earth, and it's equal to roughly 9.8 meters per second squared. Now, so if we have like a box similar to the box we have here, if we have a box, say, that's 10 kilograms, all right, there will be a force of gravity acting on it downwards that's 10 times 9.8, or 98 newtons downwards. So that's basically how you find the gravitational force on everything near the center of the Earth. But there are occasionally cases where you also have to deal with things that are not near the center of the Earth. In this case, you have to use Newton's universal law of gravitation. And the law is given by this equation here. And it's basically F equals some constant times the product of the two masses divided by the square of the distance they are apart. So what this is saying basically is if you have two masses, there's m1 here and m2 here, and then they're a distance of r apart, we can use this to find the total force, the force of gravity between them. It would just, and the larger the masses are, like the larger the force of gravity is, that makes sense. And also the further apart they are, the smaller the force of gravity is. That also kind of makes sense. All right. And the value of Newton's universal gravitational constant is given here. It's G equals 6.674 times 10 to the negative 11 meter cubed per kilogram second squared. And I think you will probably be given this on the actual F equals MA test. And so I don't think you need to remember this. All right. Now let's go on to some practice problems. So I'll give you a couple of minutes to look at these and think about them. And if you have any questions, of course, feel free to ask me and or send your answers to me after you're done, please. Oh yeah, and for the second problem, it would be nice if you could also write it in terms of g, like the mass of the Earth and the radius of the Earth. Yeah, okay, so I've gotten a couple of answers. So I will start going over these problems. So for the first problem, two objects have a gravitational force F between them. If the distance between them is doubled, what is the new gravitational force between the two objects? So for this problem, what it's basically asking is, so you have two objects, and let's just say they have masses m1 and m2, and they're separated by a distance of r. So it tells us what the gravitational force between them is, as F equals, and it's equal to g m1 m2 over r squared. Okay, but now the distance between them is doubled. So this distance is now 2r. And what's our new force? Well, this is g m1 m2 over 2r squared. But this is just g m1 m2 over 4r squared. And we can just use this value here. So now this is just 1/4 of f. So that's the answer for our first problem. And of course, at any time, please just send me a question if you're confused. If you have any questions. All right. For the second question, it asks you to find the acceleration due to gravity near the center of the Earth. So how will we do this? Well, let's say we have our mass m here, and then here's the Earth. It has a radius RE, and it has a mass ME. So what's the force of gravity between them? Well, we can use Newton's law of universal gravitation to get the force is G times the mass of the Earth, mass of the Earth, divided by the radius of the Earth squared. This divided by the radius of the Earth squared is the reason why is because That's the distance between the two centers of our objects. So normally when we have spherical objects, we usually take the distance as the distance from the center as an approximation, which is in some cases exactly correct. In other cases, it's basically almost correct. So that's the distance between their centers. And we are also assuming that the height of this object is negligible, which is why we specify near the center, near the surface of the Earth. All right, so we got our force. And now how do we find the acceleration? Well, all we have to do is use F equals ma. F equals ma, or A equals F over m. So all we need to do is divide our force here by m to get our A, which will equal to G me over r squared. And we can double check that if we plug this into a calculator, we get something like 9.82 meters per second squared, which is close to the usual like 9.8 that we're all used to. All right. Maybe just do this. And so now let's go on. All right. Normal force. So normal force is the name we give to forces that are applied by surfaces. And it has two important properties. First of all, it's always perpendicular to the surface. This is important. So if we have a surface that's tilted, then normal force will always be perpendicular to the surface. So it's not necessarily just completely vertical, but it is always normal to the surface. So whatever orientation the surface is in, like it can be a curve, and in this case it will just be perpendicular to the tangent line of the curve. All right, that's its first property. And a second property that's very important about normal force is that its magnitude, it's not really fixed. Like we don't have an equation for it like we have an equation for the force of gravity between two objects. And the reason for this is because normal force is basically the force that prevents objects from moving through a surface. So let's just say we had a table here. This is a table, and we have a box on this table. And the box weighs 10 kilograms. First of all, there's going to be gravity on this box. So what is the magnitude of the gravitational force on this box? I just did this. Yes, it's 98 newtons. All right, that's all good. But let's say there was no other force. What would happen to this box? Well, if we use F equals ma, then we'll get A is F over m, which is 98 over 10, which is 9.8 meters per second squared. So what this means is that if we don't have our normal force, then, well, what would happen to our box? It would accelerate downwards 9.8 meters per second squared. So what would happen is the box will move down, down, and it will basically just move through our table. But we know that that's not what actually happens. The box, if it's just sitting on our table, we know that it's at rest. So what happens is that there has to be a normal force, and in this case, it's equal to 98 newtons because it has to balance out the force of gravity, and it's in the opposite direction or upwards. So now if we had a table, another table, but now the box on top was 100 kilograms, what would happen? Well, there's going to be 980 newtons of gravity downwards. So in order to keep the box on the table, there has to be 980 newtons of normal force upwards. So normal force can change depending on the situation. And just as another quick example, I didn't put this in the slides, but say I had a table and we have a box that's 10 kilograms on the table. But I also push down on it. So this is me. I push down on it with 100 newtons of force. What is the normal force on the block from the table? I'll give you a minute or two to think about this. Okay, yeah, it's been a couple of minutes, so I will first talk about how you would try doing this problem. Well, the first step in most dynamic problems is going to be drawing a free body diagram, since you have to draw a free body diagram to better visualize the problem, make sure you have all the forces involved. And this is like not that hard of a problem, but as it gets more complicated, it will definitely help you just visualize everything. So, what forces are acting on this block? We have gravity here is downwards. We have the force that I applied that is also downwards. And we have the normal force. Alright, so now we have our free body diagram. Now, what's one condition that we have? It's not really stated in the problem, but it's kind of implicitly there. Well, it's that the block stays still, right? It doesn't fly off into the air, and it doesn't drop through the table. These just can't happen. So what do we know then? It's staying still, so the net force has to be equal to, well, it's equal to ma, but our acceleration is 0. So this is just 0. All right. So what does this mean? Well, it means that when we add up all of our forces, we should get 0. So let's add them up. We have Fn, um, we have Fn, the normal force, which goes upwards. And then we have Fg, the gravitational force, which goes downwards. And we also have the applied force, which also goes downwards. And this is equal to 0. So now the question is just asking us for the normal force. So we can just quickly solve for that. The normal force is just a gravitational force plus the applied force. And we know that gravity is mg. And so we get 9.8 times 10 plus 100, or 198 newtons. Alright, so that was just a quick example. Now, let's go on to another example, a bit more, or actually, no, first let's talk about scales. Alright, yeah. So, you might have encountered a problem that says like someone's standing on a bathroom scale or something. So we have a person standing on a bathroom scale. And here's the scale. Alright, so what's the reading on the scale? Well, when the problem asks for what is the reading on the scale, what they're really asking for is what is the normal force that the scale applies on this person right here. And that's just because that's how normal bathroom scales are built normally. Because if you're just standing right here, there's going to be gravity and a normal force. And if you're just normally standing still, gravity's just mg. And so if normal force has to balance it out, normal force is also mg. So what the scale is measuring is mg, and from there it can just divide by g to get your mass. So that's how normal bathroom scales work. So I have two problems here. I kind of already did one of them, but I'll give you a couple of minutes to do these problems. As always, if you have any questions, you can ask me or send your answers to me once you're done. Alright, it's been a few minutes, so I will start going over these problems. So the first one I kind of already did, and it just says a person is standing on a bathroom scale. There's going to be gravity that's mg, and it's downwards, and there's going to be normal force. And since normal force is the only other force that acts on this person, it should be mg and upwards in order to make the total net force equal to 0, because the person is standing still, which means that he or she is not accelerating, which means that since F equals ma and a is 0, F net is just 0. Alright, but now we have the second case. Alright, so the answer for the first problem is just mg. Or I guess some people said m, which is fine too, because depending on what type of scale you have, it will either report your weight in newtons, that's fine, or it can divide by gravity for you and report your weight in kilograms, or if you're in the US, it might convert it to pounds. All right, so for the second problem, we have a person that's on a scale, but the whole thing is in an elevator that's accelerating upwards at A. So what happens to this setup? Well, the person is in the elevator, right? So what does that mean? It means that the person also has to be accelerating upwards with acceleration A. So this makes the situation slightly different. So we still have gravity on the person, and it's still mg. And we still have normal force. That's what we want to find. But the net for, well, yes, in this problem, the elevator is getting faster. And is it dangerous? If it doesn't get faster too quickly, then maybe not. But just assume that the elevator's just accelerating upwards. We don't really care about what's going to happen after that. All right. So let's write F net equals ma for this person. We know the total mass of the person, and we know that the person is now accelerating upwards at acceleration a. That's our a here. But what is F net? Well, F net is the sum of all the forces, which is a normal force going upwards, and then a gravity force going downwards. Alright, so this is our expression for F net, and it has to be equal to ma. So from here, all we have to do is solve for the normal force. So our normal force is going to be mg plus ma. And this is our answer, or if you divide it by g, it would be, well, this thing divided by g. And so, yeah, this is an effect that's also pretty commonly tested. So if you stand on a bathroom scale inside of an elevator, and then the elevator starts going upwards, you'll momentarily experience a gain of weight. But, so yeah, that's also an important difference between weight and mass. Weight would be the normal force you feel, that's your apparent weight, while mass is just how much matter that makes up you. So mass cannot change unless you actually gain or lose mass, I guess. but weight can change depending on gravity because it's mg, and it can also depend on whether or not you're accelerating. So if you're in an elevator and the elevator accelerates upwards, then you momentarily gain some weight. Well, and that also works in the other direction. If the elevator accelerates downwards, then you will lose some weight. All right. So now let's go on to another problem about normal force. This one's a bit harder. So I will give you a bit more time and also give some hints as I go along. So work on this problem. As always, if you have any questions for me, just send them to me in the chat. Or also send me your answers once you're done. Alright, so it's been a few minutes, so I will start talking about how you might approach this problem. So first of all, let's draw a diagram. So here's our diagram here. And we want to draw and label all of the forces that act on this object. So can anyone tell me which forces act on this object? Yeah, okay, so there's going to be gravity since it is near the surface of the Earth. That's kind of implied. And yeah, there's gravity that's acting on this block and normal force. And there are no other forces in this case. Oh yeah, by the way, we are assuming this is frictionless for now, so no friction. But I will talk about friction later on in this lecture. Alright, so we have gravity and friction. Now, what's some condition we have? Remember, we talked about how gravity is always mg downwards. So we know what gravity is. It's just mg downwards. What we want to find is the normal force. All right. So last time we tried finding the normal force, it was just on a flat table, right? And we could just add up all the forces. But this time it's different because it's on an inclined plane, right? So they're not exactly in the same direction necessarily. They are in different directions. And they're not opposite either. So what's that condition that we had about normal force? Well, basically, all normal force is the force that prevents this block from just accelerating into the incline. So if the block like accelerates this way, for example, well, a few seconds later, it might be here. But that doesn't happen. Like the block can't go into the incline. Oops. Accidentally erased the incline. So what do we know about its acceleration? Well, if it can't go into the incline, it also can't like fly away from the incline, right? This isn't like an airplane box. So we know that it can't go into the incline and that it can't fly away from the incline. So its only possible acceleration is down the incline. Or so what does this really mean? Well, to make this easier, we can then break down the gravity into components. So there will be different components here. And by geometry, well, we can find that this angle is theta. If you want, I can do a quick explanation of why. So gravity is downwards, which means that it's a right angle, it's at a right angle from horizontal. And we also know that this thing, the vertical axis in our case, first of all, we're going to call this our horizontal axis and this our vertical axis. And this is because it'll just be much easier to add up all of the forces, as we'll see in a moment. Alright, so if this angle is theta, well, this angle is 90 minus theta. But we know that normal force is always perpendicular to our incline, right? So this is a 90-degree angle. These are 90-degree angles. So now we can just use simple geometry to get that this is theta. Alright. So now that we know the angle, we can break it into components using trigonometry. So this component is mg cosine theta. This vertical component here. And this horizontal component here is going to be mg sine theta. Alright, so now we can solve our problem. Because what do we know now? Well, after we rotate our axes, this is basically what it looks like. There's a normal force here, and then there's gravity here. It's at an angle theta, and we know its components are mg cosine theta and mg sine theta. Alright. And we've also established that it has to be accelerating in this direction, which means that the forces in the vertical direction have to cancel out. So what this means is that our normal force has to match the vertical component of gravity, or mg cosine theta. Now that these two components sort of cancel out, the only component we're left with here is our mg sine theta, and that will be our net force. Okay, so if we go back to what the question was asking, it was asking, we want normal force. So we have normal force right here. And we want the acceleration of the block. Well, to get acceleration is just F net over M. So this is g sine theta. And as to which direction it is, well, we already established that it just accelerates down the plane. Alright, so these are our answers. Alright, and with that, I will actually start our short break since it's almost 2:30. So I will come back around 2:35, and in the meantime, I guess I'll put my explanation back up so you can look at it. And also, if you have any questions, you can always send a message to me in the chat. And I will try to answer it, or maybe I'll answer it after the break. If, yeah. Okay, it's 2:35, so I will get started again. Okay, so now let's talk about spring force. So, what is spring force? Well, as you might have guessed, it's just the force from a spring. But we actually have some equations for that too. So, most springs obey Hooke's law, which basically says that how much you stretch it, well, the more you stretch it, the more force it pulls back on you. So it's directly proportional to the distance you stretch it, and the constant of proportionality is just K. It's called the spring constant, and it's different for each spring. So, as an example, we have, let's say we have a spring here, and normally, like when it's not stretched out at all, its length is 2 meters, let's say. All right. Now, if you stretch it to a length of 3 meters, then what will the force be on this object? And also, let's just say the constant here is 100 newtons per meter. That's around the same order of magnitude as like your ordinary springs. Well, to do this problem, it's actually very simple. So first of all, you want to get x, how much you stretched it. You stretched it by 1 meter, and so now your force is just negative kx, is negative 100 newtons. And the reason why there's a negative sign there is just to indicate if you stretched it to the right, then the force will be back here to the left. And in the same way, if you compressed it, so now it's only 1 meter, then you'll also have a force of 100 newtons, but it will be in this direction, which kind of makes sense intuitively. All right. So now I have some example problems here. So I will give you a few minutes to think about these, and I'll also probably end up giving a few hints along the way. So just do these problems. If you have any questions, ask me, and if you're done, send me answers too. Oh, and also for number two, by connected in parallel, I mean if you have like say something here, and then there's one spring that's has constant K1, and then another spring that has constant K2, then we have this whole thing acting as one spring. So we want to find the effective spring constant of this. And also, I would like you to do it in the case where they're connected in series as well. So if there's a spring with constant K1 right here, it's connected to another spring with constant K2, and these two are also acting as one spring. All right, so it's been a few minutes, so I will first go over number one, and I'll see if that gives you some idea on how to do numbers two and three as well. All right, so let's go back. So first of all, number one says we just have a spring and it has constant K. And we cut it in half and we want to determine the new spring constant. So we cut it right here. And what we're basically left with is just two springs. All right. But now what happens? Well, just let's just suppose that they were somehow magically connected again right here. then they would basically act as a single spring. And that single spring should also have a spring constant of K, right? But now let's look at what happens when the spring is compressed by some distance x. So it's compressed by x. And what will happen is that this spring will be compressed by x over 2, and this spring will also be compressed by x over 2. Right? But we know that since the combined spring acts as a single giant spring with spring constant k, it has to apply a force of kx. And that force just comes from this spring right here, right? So this spring right here should have a spring constant k equals F over the displacement, how much it's compressed, which is kx over x over 2, which is 2k. So actually, if you cut a spring in half, the remaining two springs will have twice the spring constant. All right, so let's go back to our number 2 and 3 and see if that gives you any more ideas on how to solve these two. It's been a while. So actually, I will go over number 3 first because I think it's a very important conceptual question. So in number 3, we have a spring here. It has a spring constant of 10 newtons per meter. All right. Now we have two people, Alice and Bob, and they're both pulling on the spring. So Alice is pulling at 3 newtons, and Bob is also pulling with a force of 3 newtons. So it asks us to just find the resulting length of the spring. Now, a lot of you said, well, this is easy. All we have to do is take the total force, which is 6 newtons, divide by 10. This is 0.6. So the resulting length should be 2.6. But this is actually not the case. And I guess the reason why is sort of the spring force. It's kind of just, you can think of it like a property of the spring, right? So if your spring is stretched, let's say 0.6 meters, then it will have to pull on something with 6 newtons of force. But what actually happens here is, let's just look at our string for our spring for a moment, and just have it stretch x amount of distance. So there's going to be kx like force in the spring. So what happens is that if you hold it from here, there's going to be kx here in that direction. If you hold it from here, there's going to be kx in that direction. So it really doesn't matter that you're holding it in two places. The force is going to be kx in both places. So really what the answer here should be is that this isn't, we don't take the total force, we just take the force that is applying. So this becomes 0.3, and then this becomes 2.3. So the answer would be 2.3 meters. All right. So now on to number 2. Number 2 is basically asking us to find the effective spring constant of these two situations here. All right. So how will we do this? This is sort of similar to the situation when we cut our spring in half. So let's do the situation where they're in parallel first. So we have K1 here and K2 here. Now let's say it was compressed a small distance of x, while this spring here was compressed a distance of x, and this spring here was also compressed a distance of x. So what does this mean? Well, it means that our spring here, will apply a force of kx in this direction, k1x, and our spring here will apply a force of k2x. Alright. So what does that mean? Well, effectively, what that means is that these two springs push on this with a combined force of k1 plus k2 times x. So our effective spring constant here is just k1 plus k2. So now with that, I want you to think for a few more minutes about how to do the case where they're in series. And you can use a very similar approach to do this case. And as always, if you have any questions, please just send a message to me and ask them, and I will do my best to explain. And also, if you finish, please send your answers to me as well. Alright, it's been a few minutes and I didn't receive any answers, which means I should probably give some hints. So, like in the previous problem, we want to consider what happens when we just compress this a small distance x. It's compressed that way. So what will happen here is that, well, both of these springs will get compressed, but they're no longer just compressed by x anymore. So since we don't really know how much they're compressed by, let's just assign them to variables. So let's say the first spring was compressed by x1 length, and the second spring, well, that spring was compressed by x2. So can anyone think of some kind of equation we can write? Like, what's the relationship between x and x1 and x2? Yeah, that's right. So the total compression of both springs was x, which means that if we add up x1 and x2, that has to be equal to x, the total compression of the strings. Alright, that's good. We have one equation, but we have two unknowns, so we need to write a second equation. Um, so let's look at this point right here. Let's enlarge it. This is that point right there. What are the forces on this point? Well, it's connected to two springs, right? And each one of the springs are compressed. So it's going to feel two spring forces. So there will be a spring force this way that's equal to K1x1. And then there will also be a spring force this way that's equal to K2x2. Alright. So we know that there are two forces on our point there. Now what's one condition that we can get? Because these springs, like, they're in equilibrium, right? So if there's a net force on this point, it'll just move, it will move around, and then one of the springs might get more compressed, the other one will get less compressed, and it'll just keep moving around until it's at equilibrium. And then it won't have a force anymore, so it will stop moving and it'll just stay there. So what we get here is that we have to have K1 x1 equal to K2 x2. Alright, so now we have our two equations and we want to solve for x1 and x2. So now I will give you a couple of minutes to solve for x1 and x2 and tell me what you get. And of course, if anything here confuses you, feel free to just send me a message and I will explain it again. Alright, it's been a while, and this is just some quick algebra, so I'll go through it very quickly. So first of all, we can just choose, for example, k1 to eliminate, x1. So k1 x1 equal, let's multiply the first equation by k1. k1 x1 plus k1 x2 equals k1x, and we have k1 x1 equals k2 x2. So now let's substitute this in. We get k2 x2 equal plus k1 x2 equals k1 x1. No one here, just x. Alright. And this means that x2 is k1x over k1 plus k2. Alright, so we solved for x2, and we actually can go from here straight to the answer. We actually don't need to solve for x1 again. But if we wanted to, we would just multiply x2 by k2 over k1. So x1 would be k2, x over k1 plus k2. Alright, but from here to get to the answer, well, we just need to find the force here that it's pushing on our plate here, I guess. So, but that's just k2 times x2, because that's just the spring force we have of this spring. So now we get our answer of k1 plus, not plus. Our answer should be k1, k2 times x over k1 plus k2 is the spring force, which means that the total k is just k1, k2 over k1 plus k2. Alright, and that's our answer. So now I will go on to talk about tension. So tension's like just the force of a string. I'm sure we've probably all felt this at one point. Or it's just you pull on a string and the string pulls back on you. And so if you have a lot of the time, we'll just be talking about massless strings. Just assuming that the string has negligible mass. And what this means is that the tension throughout the string is always going to be the same. Alright, so if we have a string here and we're pulling on a box, if we're right here and we pull on the string and the string applies some tension force that way to us, then it will apply that same tension force to the block as well. So these two tensions will be equal. And to see why this is the case, it's sort of similar reasoning with our springs. And the reason is, if we consider a string here, this is our string. We zoom in, so it looks like this now. And we consider a small, tiny element of our string here. Now the tension on the right side, let's say it's T1, and the tension on the left side is T2. What would happen if T2 is not equal to T1? Well, there would be a net force that's not equal to 0. But since we assumed our string was massless, this would basically mean that our acceleration has to go to infinity for this to happen. So the moment that there's a difference in tension, the acceleration will go to infinity, which is bad. Like, it's not physical, like, it just doesn't happen. And also, say this tension was greater, well, then we would just see our mass element accelerate to the left. And then that will make this segment less stretched and this segment more stretched. This segment more stretched. And this segment will be less stretched. So T2 will go down and T1 will go up until they equalize themselves. So that's the reason why the tension throughout a massless string is constant. And we can also look at tension in our figure here. So we have some gravity force here going downwards. And what's holding this box up is just a tension force. So we would say the tension in the string would be equal to mg. And this is because it has to support our box that's hanging from the ceiling. Alright, now let's talk about Atwood's machines briefly. So an Atwood machine is just a fancy name for a system of pulleys. And right here, we have the most simple case of an Atwood machine. So we have two masses, m1 and m2, and we want to find their acceleration. So with Atwood's machines especially, it's very important to draw free body diagrams and also just to reason out like what are the objects involved, what are the forces involved. Just write F equals ma for each object, and you should get a system of equations which you can then solve to get your answer. So I'll give you a few minutes to think about this. And as always, if you have any questions, just ask me. And if you're done, send me your answers. Alright, it's almost 3:30, so I will just go over the solution quickly. And I do have a few more problems, but hopefully I'll be able to go over some of them. And if there are any that I don't you can always, I'll just show them to you. You can think about them afterwards, and I will probably talk about them in the next lecture. Alright, but for this problem, what we have is basically we have a pulley here and two masses, M1 and M2. Alright, so first let's look at M1. So whenever we approach this type of problem, we always first draw free body diagrams. So what are the forces on M1? Well, there is gravity, M1G, and there's also tension from the string. And on M2, there's also gravity and tension on the string. And these two tensions are equal because we're assuming it's an ideal massless string. Alright. But, so we can write F equals ma. We have M1a equals the net force, which is T minus M1G. And we also have M2a is equal to M2G minus T. And these two accelerations are actually the same thing. Oh, and also the reason why I wrote them backwards is because if this one's accelerating upwards, this one must be accelerating downwards. But, okay, so these accelerations, these two A's are actually equal. And we can think of this as sort of, some people call it conservation of string. So the idea behind this is that this length, the total length of the string can't change. So however much this one goes up, this one has to go down by that exact same amount. Which is why if this one's accelerating upwards, well, this one just has to accelerate downwards at the exact same rate. Alright, that's cool. So now we have a system of two equations, two unknowns. We can just add them up and solve for A, which is what we wanted to find. And we should get that A equals to M2 minus M1 over M2 plus M1 times G. And for direction, well, this one will be going upwards, and this one will be going downwards, assuming that M2 is greater than M1, and otherwise this one will be going upwards, and this one will be going downwards. And that's accounted for in the sign of our thing. Alright. Now let's go on to friction. So I will explain this very quickly. What friction is, basically, we have two types of friction, static and kinetic friction. So what happens with kinetic friction is that the two objects, they're slipping, so they're moving relative to each other. So let's say we have a block on a floor that has friction, and it's moving that way with some velocity, but the key is that it's moving. Alright, there's going to be gravity on this object, and there's going to be a normal force. But there's also going to be friction. And the key equation here is that the frictional force in this case is some coefficient times the normal force. So higher normal force means higher friction force. And we sometimes call this mu k, this constant. It's the coefficient of kinetic friction. Kinetic meaning that they're just moving relative to each other. Now, static friction is slightly different. Static friction is when the object's at rest. So it has gravity as usual, and it also has normal force. But what happens is that with static friction, if I give this box a little push, there can be friction force that acts against my push to keep it still. And I can keep on pushing harder, and the static friction force will get harder as I push harder until it reaches a maximum. So the maximum it's also similar to kinetic friction. It's proportional to the normal force. But the difference here is that it's now mu s, the coefficient of static friction. And sometimes this can be different from the coefficient of kinetic friction. Alright, and I have an example problem here, which I'm kind of over time, but I will go over very briefly. So we've seen a similar problem to this before, where there's going to be gravity and a normal force. We've calculated these already in the previous problem. This is going to be mg cosine theta, and this will be mg. And we'll have our components, so there will be mg sine theta in this direction, mg cosine theta in this direction. For it to stay still, there also has to be a friction force in this direction, and it has to balance out this force. So it will also be mg sine theta. This is our friction force. So what's our mu? Well, it's just our friction force divided by our normal force, which would be mg sine theta over mg cosine theta. Let's move this over somewhere. Alright. And this simplifies to just tan theta. And, that would be our answer. So now I have two example problems. One of them is from the F equals MA, and the other one is from just the Morin book. It's a modified version. So I will just show you these. You can take a picture if you want. And I will probably go over these in the next lecture. Alright, other than that, that's it. If you want extra practice, you can go to those pages of Morin's book and do some problems. And other than that, thank you for listening, and I will see you in the next lecture.